In an example from last time, we had methane that was powering a turbine, and we wanted to figure out what the maximum amount of work that we could get out of this turbine is. The methane enters at 10 bar and 600 Kelvin and exits at 2 bar 400 Kelvin. Recall that we simplified the energy balance last time, so it's just a quick review. So by an energy balance, I got back that the shaft work per unit mole was equal to the change in molar enthalpy. And just as a quick aside, you could also do an equivalent energy balance. You could have said shaft work per mass was equal to h hat 2 minus h hat 1. And these are equivalent. Mostly in thermo, we work on a per mole basis. But either one of those will work. And then we set out to find what H2 minus H1 is. So remember, we don't have, well, assuming we don't have a steam table for methane, I'm sure if you look hard enough on the internet, you could probably find one. That would be the number one way to go about solving this problem, is just to go find a table where you could look up, given what the pressure and temperature for methane was, finding what H under bar 2 and H under bar 1 are. That would just give you the answer. But we're going to assume for the purposes of this problem that that is not possible. So we need to model this delta H with a mathematical model. So how do we find what this delta H is in the absence of experimental data? And using some of the Maxwell relations and some of the calculus tricks that we learned a couple times ago, we got down to the following expression. We said that dH was equal to Cp dt plus V plus T dV dt at constant P dP. All right, so you should practice deriving this expression yourself without looking at your notes at all. If you can't derive this expression from starting at the very beginning, which is saying that H is a function of T and P, and remember the rationale for why we say that H is a function of T and P as opposed to anything else, it's because we have information on T and P. I would encourage you to go back and rewatch the video and double check. So derivations are very useful to be able to do in thermo for solving new problems rather than just memorizing these solutions. It's actually a weird trade-off in thermo, just as a quick tangent. Sometimes you will want to really be able to derive stuff, and other times it's not worth your time, and it's easier to memorize stuff. So it's really important to strike a balance. I think that the best is when you're able to derive something if you needed to, but you don't necessarily have to derive everything brand new every single time. Sometimes you can start from pre-derived stuff, and that's just as a way to expedite your problem-solving process, but you should be able to do it if asked. Remember what the problems with this expression were. That Cp is not Cp star. So in the back of the book, you have an appendix where it gives you what Cp is. It doesn't explicitly say that it's Cp star, but Cp star is only for an ideal gas. And Cp here, because we're going from 10 bar to 2 bar, we cannot assume ideal gas. So the Cp in the back of the book is not valid. Cp in appendix, not valid at these high pressures. Also, as a quick aside, in your notes, you may have a different expression here. In your notes, you may have dsdp at constant T. Remember, I just did a quick Maxwell relation there, because dsdp at constant T is harder to define than dv dt at constant P. So remember, anytime we have V, T, and P together, that's what we want, because those are the three variables that we can measure. All right, so how do we go about solving this problem if we can't use the Cp then? Let's take a few steps back and just try to think about what we're trying to do. We're trying to calculate the change in enthalpy as we go from state 1, which is 10 bar 600 C, to state 2, which is 2 bar 400 C. We just tried to calculate it directly, and we ran into a roadblock. So this path doesn't work because it requires us to know what Cp is. And we don't necessarily know what Cp is if we can't assume it's an ideal gas. But we can use the information that we do know what Cp is if the gas were ideal. And we could also use the fact that enthalpy is a state function. So instead of going directly from state 1 to state 2, let's try and construct a hypothetical process path, which we can do because H and enthalpy does not depend on the path taken. So instead of going directly from 10 bar 600C to 2 bar 400C, let's try and break it up into a couple of different steps. So let's instead first try going down to a state in which I can't assume an ideal gas, and that'll allow me to use what CP is. So I'm going to call this state 1 star. I'm going to call it state 1 star to denote that it's state 1, but assuming ideal. And my P1 star here, I'm going to lower the pressure into an arbitrary amount until I can imagine that the gas is ideal. So let's just try a low pressure, 0.1 bar. Relatively low. I'm going to assume at that low pressure, I do have an ideal gas. Literally, so I could go all the way down to 0 bar, but then we're getting into theoretical stuff. So I want to pick something that's still tangible. Temperature is going to remain constant in this first step. So this first step is decrease P at constant T. And this is step 1. All right, so I may imagine that I could calculate what delta H is for this process. All right, we'll talk about that a little bit later, but because I'm only changing pressure, not changing temperature, I'm not going to have a CP term. So the derivation of this delta H is going to be the same, but because this dt is going to go away, I'm going to be left with just that second part. And just as a quick foreshadowing, this is what we mean when we say departure function. This whole thing in the brackets designates the departure of this gas from ideal conditions. So at 10 bar, which is different than the low pressure at which ideal gas is constant, whatever the value of this is going to tell us how far away we are from ideal gas. We'll talk about that in a little bit more in one moment. But I need to go through some more steps in this hypothetical process path. So I need to now that I have a low pressure, I can now change my temperature. So I could say this is now going to be state 2 star. And at state 2 star, my pressure is going to remain the same. And if my pressure remains the same, then I can use CP star. But my temperature now is going to decrease to my 400 K. Shouldn't be 400 degrees K, by the way. It should just be 400 K, or 600 K. This is step 2. And this is decreasing temperature at constant P. And we'll be able to calculate a delta H for this. This should just be the integral of Cp dt. And that is because for this one, dP is constant. There is no change in pressure. I think I have my brackets messed up. Yep, I do. Apologies for that mistake. This bracket should be there such that if dP goes to 0, this entire term goes to 0. So go ahead and fix that in your notes. Now I'm going to have one last step where I go from state 2 star back up to state 2. So this is an increase in pressure at constant T. And in step 3, it's just going to be the reverse of step 1. So I'm going to be able to calculate what delta H3 for that process is. And again, because this is H is a state function, I can say that delta H overall, this is the delta H, that's the direct process from state 1 to state 2, is equal to delta H1 plus delta H2 plus delta H3. So I've made it a little bit more work. Instead of going directly, I now have to do 3 separate functions and add them together, but it's going to get me a useful solution. So real quick, I want to illustrate that these things are equivalent if I write these a little bit differently. So delta H is going to be the change in enthalpy from state 1 to state 2. All right, and delta H1 is going to be the change in enthalpy from state 1 star to 1. So it's going to be H1 star minus H1. Also, a quick note on the notation I'm using. I really don't like how Sandler does IG for ideal gas, so I like to use a star. Something in my mind, like I think of a star when I think of ideal gas, and I think HIG is sometimes difficult to read, especially with handwriting. So I'm going to use stars for my ideal gases. Delta H2 is going to be the change in state 2 star from state 1. 1 star. So H2 star minus H1 star plus delta H3 is going to be H2 minus H2 star. And then if I look and see what cancels out, so I've got an H1 star in the first term, cancels with a minus H1 star in the second term, and an H2 star cancels with an H2 star in the second and third terms. And I'm left with H2 minus H1. So this tells me that these two things are equivalent. All right, perfect. So how do we go back and find what delta H1 is? So if I want to find, or you know what, I'm going to start with delta H3 because 2 minus 2 star is how it's actually defined. So I'm going to start at the bottom. So delta H3 is H2 minus H2 star. Try not to get confused with my notation. So this 3 here denotes it's just step 3 in my hypothetical process path. And the 2 and 2 stars refer to my 2 is the actual ending process state, and 2 star is one of my hypothetical process states. So I can use that expression that I derived above, right? So I can say, I can go differential form, and I'm just going to copy this exact thing from above below. So it is Cp dt. I just realized you don't have to sit here and watch me write every single thing. If I just copy this down, I'm going to try and shorten the video by doing that as much as possible. All right, in step 3, dp was equal to, I'm sorry, dt was equal to 0, right? Because in step 3, we have a constant temperature. So Cp dt is going to be 0 since no T change in step 3. And then we are just left with simply the second term, which is going to be called our departure function. So this is the literal definition of a departure function, is the change in any property, doesn't necessarily have to be enthalpy, from an ideal state. So it's going to be dH, and we're going to integrate that from state 1 to state 2. So that is going to be H2 minus H2 star. It's equal to the integral of V plus T dV dt at constant P dP. And the conditions for this, so we need to carefully specify our temperature and our pressure here. So this is going from at state 1, sorry, should be more clear, state 2 star to state 2 is our limits of integration. No, I have it backwards. State 2 to state 2 star. Wait, no, I did have it right. State 2 is on the top, state 2 star is on the bottom. So 2 star is T is equal to 400K. What was my temperature? 400K. And P is equal to 0.1 bar. And T is equal to 400K. P is equal to 2 bar. Sorry, 2 bar. Hopefully you should see that step 1 is just the same thing as step 3, but in reverse. So I want to note that this is our departure function. And there will be 2 kind of departure functions for this process. So step 1 is the same thing, but in reverse. And here our delta H is going to be H1 star minus H1. So the only thing I have to remember is that the limits of integration are going to be flipped, or I can account for that in a negative sign. It's important that you don't do both, so do one or the other, but not both. So it's state H1, state H1 star, dH is equal to, all right, that's settled. So step 1 and step 3 are the same. They're just kind of mirror images of each other. All right, now step 2, I'm going out of order here. I'm trying to do it in a logical order, and that happens to not be chronological. Remember, step 2 from up here was a change at constant pressure of temperature. So if I start with the same formula again, now dP is going to cancel, and dH, which is going to be H2 star minus H1 star, is the integral of dH is equal to the integral of Cp dt. And T is going from 600 to 400. All right, so putting it all together and generalizing, right? The idea is I want to find a direct expression for H2 minus H1, and I couldn't find that directly. So I had to construct a hypothetical process path by which I did 3 separate steps. So I tried to write it such that they are directly analogous to each other. And also, I've gone through and I've said P is equal to 0 because that mathematically that's more proper. You don't want to arbitrarily set pressures 0.1 versus 0.01, right? They're similar things, but you want to go all the way to 0. All right, one last thing, and then we'll wrap up this video. This entire equation, you'll notice, is in terms of stuff that we know. So the first term is V, T, and P explicitly. The second term is Cp star, which we do have information on. And the third term is also Tv and P. So no problem in solving it. The issue with this particular form is we need an equation of state in order to solve it. And if we have an ideal gas equation of state, the problem is easy, right? So we can say dV dt at constant P is equal to question mark, and we could say that V is equal to RT over P, and therefore the partial of V with respect to T is R over P. And then we can multiply that by T again, and then the whole departure function, V minus T, R times P, is equal to RT over P minus RT over P is equal to 0. All right, so this is helpful in illustrating that for an ideal gas, the departure function is 0 because there is no departure from ideal conditions. The issue is what if we have a more complicated or cubic equation of state here? So let's take, for example, the van der Waals equation of state. All right, we haven't talked much about our review of equations of state, but the van der Waals equation of state says that P is equal to RT over V minus B, and B is a parameter, minus A is also another parameter, minus A over V squared. Now, in order to evaluate the partial of V with respect to T, we would need to solve this expression for V. So you'd have to fiddle with the algebra a little bit, and you should find that in the end, if you try and solve for V, it's very difficult because this is a cubic equation of state. In other words, if you tried to solve for V, you would find that V to the third power is in it. So it's harder to FOIL and very difficult to solve by hand. So to avoid that problem, I'm not going to show you the derivation of this, but you should be aware of an analogous form of the departure function. And this is going to be in section 6.4 of Sandler. And I'm not going to show you the whole derivation. I'm just going to show you what it is. I encourage you to try this on your own before you read it. So try and see if you can adjust the expression that we had for the departure function to this form. So this is just going from H minus H star. It's equal to RT Z minus 1, and Z is the compressibility. So there's some more simplification needed in this form, plus the integral, and because I'm changing my terms around, instead of T and P, I'm now going from V. So analogously, as P goes to 0, V goes to infinity. Those two things happen together. V is equal to V is a function of T and P. And the form is now T times dP dt at constant V minus P times dV. And in this form, it's still in terms of stuff that we know, V, T, and P, but now we have the partial of P with respect to T. This does not require us to solve the equation of state for V. We can use the equation of state solved for P already and use it in this form. So this form of the departure function is a little bit more handy to use. And this is the end of this video, but at the beginning of next video, we'll apply this exact definition of the departure function to that methane problem in the turbine.